Hmm. Trigonometry, Chapter 2, Acute Angles and Right Triangles. Section 4, Solutions and Applications of Right Triangles. Video 1, Significant Digits. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous section, we explored approximations of trig functions. We learned about how to use a calculator's trig and inverse trig functions. We also explored a few applications. In this section, we discuss solutions of triangles in general, and in this video, we discuss the concept of significant digits. Question: how tall are you in inches? Chances are your answer is wrong. Well, maybe wrong isn't the best adjective. More like your answer is imprecise. For example, I claim to be 5 foot 10 inches. That's 70 inches. But when I measure my height, I'm limited by the precision of the device with which I'm measuring. When I claim to be 70 inches, I'm really saying my height is between 69.5 inches and 70.5 inches. When I measure my height, I use 1 inch precision. Technically, I could be more precise because the measuring device I use has precision up to 1/16 of an inch. If my height was approximately 70 inches and I used the most precise measurement I could, then I'm actually saying my height is between 69 and 15.5 sixteenths of an inch and 70 and 0.5 sixteenths of an inch, or 69 and 31/32 of an inch and 70 and 1/32 of an inch. For our purposes, we will assume that any measurements we are given, either length, angle, measure, or any other continuous value, are measured to a certain number of significant digits, or SDs. Significant digits convey the precision to which a measured continuous value was obtained. For example, if we are told a measure is 125 feet, this measure has 3 significant digits. However, if it were measured as 124.75 feet, then it has 5 significant digits. Where significant digits become a little unclear is when you have a whole number with trailing zeros, such as 3,900. Is this measured to the nearest whole number, or the nearest 10, or to the nearest 100? In this case, we assume the least precision possible and say that 3,900 has only 2 significant digits. To indicate more significant digits in such a case, you place a bar over the last significant digit, like this, 3,900 with a bar over the first zero. This number has 3 significant digits, 3, 9, and that first zero. Also, if a whole number ends in zeros and they are all significant, we can write the number with the decimal point at the end without any digits following it. So 3,900 has 2 significant digits. With the bar over the first zero, it has 3 significant digits. With the decimal at the end with nothing following it, it has 4 significant digits. Decimal at the end. As for numbers with digits after the decimal place, leading zeros are not significant unless there is a non-zero digit to the left of the decimal place. So for example, 0.0025 has only 2 significant digits, but if we put a 7 in front of the decimal, now all 5 digits are significant. Also, any trailing zeros in a decimal are significant. So 0.00250, the 250 are all significant digits. We change the 0 in front to a 7. Now it has 6 significant digits. Concerning angle measures in degrees, minutes, seconds, we locate the last significant digit in the smallest measure and assume all digits are in larger measures are significant. For example, 50 degrees 30 minutes has 3 significant digits. The smallest measure is minutes, which has 1 significant digit, the 3. The larger measure has 2 significant digits. Lastly, the rules for number of significant digits in the answer to an arithmetic problem are sometimes inconsistent and unreliable. Precision is usually reserved for measurements. However, in some circles, here are the rules. Number 1, when multiplying or dividing, round to the same number of significant digits as the measured value with the fewest number of significant digits. And number 2, when adding or subtracting, a little grammar mismatch there, but that's okay. Use the lowest place value as the most imprecise measurement has. It's not worded too clearly. I'll show an example. For example, when multiplying 0.002 208 times 3.2 and focusing on significant digits, the actual answer is 0.6656. However, concerning significant digits, the least precise measurement, 3.2, has only two significant digits. So we would round our answer to two significant digits and get a product of 0.67. When significant digits are concerned, a product or quotient cannot be more precise than any value used to calculate it. Now, for something like 12,000 plus 375, the least precise measurement is the 12,000. It only has two significant digits. The lowest significant place value in this number is the thousands place. We have 10,000, but lower than that is thousands. So the sum, 12,375, is rounded to the thousands place. This gives us 12,000 plus 375 is approximately 12,000, which as a theoretical mathematician makes me cringe just looking at it. But that's the rule. Now you try. Pause the video and try the following. 1 through 3 are to determine the number of significant digits. 4 and 5 are to do a couple of simple calculations using significant digits. All right, here's your fair warning. If you haven't paused the video yet, solutions in 3, 2, and 1. The last two are a little cringeworthy in my eyes.